In this course, we're going to be using simplified lambda-based design rules. Now imagine in one technology we have a minimum transistor drawn here, where we have the minimum transistor length being 0.4 micrometer. We have the minimum transistor width being also 0.4 micrometer, and we have the minimum poly overlap being 0.3 micrometer. Now we have another technology which is a little bit more advanced, where we have the minimum transistor drawn here. Here we have the minimum transistor length being 0.2 micrometer. We have the minimum transistor width being 0.3 micrometer. And we have the minimum poly overlap here being 0.1 micrometer. Now, if you want to change designs between these technologies, you need to learn a whole new set of design rules, and that can be quite cumbersome. So the lambda-based rule attempts to abstract the actual micrometer or nanometer numbers into an abstract number or dimension lambda, and then choose a conservative set of design rules that can be scaled. Now, for instance, if we scale all of the dimensions according to the minimum transistor length, which is common, then we can see that relative to the minimum transistor length, the poly overlap in technology 2 is smaller than it is in technology 1. And we can see that the minimum transistor width in technology 1 relative to the minimum transistor length is smaller in technology 1 than it is in technology 2. So we can construct a conservative layout where we don't break any of the minimum rules in either of these two rules, looking something like this in technology 1 and something like this in technology 2. So what we have done is that we have increased the minimum transistor width in technology 1 to 0.6 micrometer, such that the ratio between the minimum length and the minimum width is the same in technology 1 as it is in technology 2. And what we have done in technology 2 is we have increased the minimum gate overlap like this, again such that the ratio between the minimum gate overlap in technology 1 and the minimum channel length is the same as the ratio between the minimum gate overlap in technology 2 and its minimum gate length. And with that, if we can do this scaling, it makes a slightly conservative design, but then we will really only need to learn one set of design rules, and we can abstract all the dimensions into a dimension called lambda, where the number of microns that a lambda equals depends on the technology we're going to use. So with that, we have an example of some lambda-based design rules here. Now, this layout makes it possible to show the core design rules for transistor. Now let's have a look. The minimum gate overlap is 2 lambda. The minimum active extension beyond the gate is 3 lambda. The minimum spacing from the active for poly contact is 2 lambda. And you're not allowed to have contacts on top of the transistor, because then you don't know if it's a contact to the poly or contact to the active. And the minimum distance from the active contact to the transistor is also 2 lambda. The minimum contact dimension is 2 lambda, except this is not actually a minimum dimension, but the contact has to be exactly 2 lambda by 2 lambda. This is the typical rule you have for contacts, that these are not minimum but exact dimensions. But this is usually the only exception to the minimum rules. The minimum poly width, which is the same as the minimum transistor length, is 2 lambda. And the minimum spacing between polys, which is also the minimum distance between two transistors, is 3 lambda. the minimum active to unrelated poly is 1 lambda. And returning to the contact, the minimum active overlap of the contact is 1.5 lambda. Likewise is the minimum poly overlap over the contact 1.5 lambda. So these are the basic transistor design rules. Now there's also rules relating to the N plus and P plus active regions, the N wells. There's rule related to the metals and the VS, but you can look that elsewhere. The principle is the same. Now when it comes to working out the actual physical dimensions for a given process, what you do then is assign lambda to a certain dimension. Now for instance, in a 0.18 micron technology, you would normally assign lambda to be equal to 0.1 micron. Now that means that the minimum transistor length you can draw is actually going to be equal to 0.2 micrometers instead of the technology limit, which is 0.18 micrometer. And this is a cost that you pay for having simplified set of design rules that you can't get the last 10% of the performance out of the chip. Now likewise, if we were having a 90 nanometer technology, for instance, which is 2 technology nodes smaller than 180 nanometer, then we would assign lambda to half the dimension as what we had before, so setting lambda equal to 50 nanometer. And that would then mean that the minimum transistor dimensions we could draw then would be equal to 0.1 micron, or slightly larger than the 90 nanometer technology will actually allow.